In this video, we're going to introduce another technique for process scheduling. This time what we'll introduce is something called round-robin scheduling. Now this idea is basically going to be, well, it's going to be different than everything else we've seen before. So here what we're going to say is the following. Imagine I have a set of processes, right? So let's say I have 4 processes. They all have kind of a different, amount of time that each one we want to request. Instead of finding basically some ordering that says, oh, run this process, then this process, then this process, then this process, instead what we'll do is we'll cut them into little pieces. We'll define what is called a CPU time slice. So a time slice is going to be the amount of time I give to a process before I move along and give time to another process. So I'm going to basically go around. I'm going to go round robin, right? You can imagine I'm going to circle each of these processes, giving them, 5 units of time, 5 units of time, 5 units of time. The point is, I'm going to let them run for a little bit of time that I specify ahead of time, and then I'm going to move on to another process, right? So instead of executing the process, kind of in one go, I'm going to do it in little slices. The hope here is I'll minimize basically my waiting time. My waiting time should be lower because I'm going to give each process a shot at running on the CPU before the ones have completed. The other thing is that when we do this, right, hopefully we can improve response time because every process is going to have a little bit of CPU sent its way, right, so it's able to do something, and maybe we can get a response to the user, right, so the user would be rather happy about that. So yeah, that's our basic idea for round robin, right? Take my CPU, right, decide of this time slice, right, or time quantum. It's a little amount of time that I'm going to basically give to each process in turn. I'll just go around to all of them that are running, right, and give them time, as I can, right? I'll go in a circle if you would, right, giving a little bit of time, a little bit of time, a little bit of time, right, until everybody kind of has their needs satisfied. So let's take a look at an example here. So here we have 3 processes. So we have process 0, 1, and then 2, right? Those are our 3 things. We're going to try basically scheduling these out. When we're doing round robin, right, we actually need to specify a little bit more information. We need to specify the time quantum. So this is basically how I slice up my process. I'm going to slice them into basically units of 5. And so when I say that, right, what happens in the graphic, right, is that, for example, I have basically my P0 of size 10, right, my burst size 10. What this becomes, right, is all of a sudden in my diagram, this should look like, I have basically a P0 of size 5 and another P0 of size 5. Right, I have multiple things. So repeating that for a second, we can look at P1. P1 is already of size 5, so P1 basically ends up being just one block, right? It ends up being one block of size 5. And let's assume that's a block with like right corners for angles. Then we have a third over here, P2. P2 has basically of length 8. For that, we'll slice it into 2 pieces, and this will become basically a piece of so this was 5 over here. This new one we'll create for P2 is also of length 5. That one's 5, and it'll actually have a second piece of length 3. Right, so we're basically slicing the process up right into pieces that are most 5 long. Now I have these pieces. That's kind of what I'll end up using to draw my overall diagram of how things work. So what's going to happen here, right? My diagram is I have basically P0's first block runs, right? So this one runs, and you see that over here, right? That's this one here. Then P1 runs, right? That one runs. You can see that over here. Then the P2's first block runs. You can see that one over here, right? So this is good as well. And that's basically one round, right? So we've gone around every process, giving it 5 increments of time, right? That time quantum of 5 is basically declaring, oh, as you go talk to each process, give it 5 units, right? It's allowed to do this much work before you can move on and go talk to somebody else, right? Go give somebody else CPU time. So we have that kind of split up all over the place. So what do we want to do next? Well, at this point, right, we basically have given every process a shot. We want to start a new round. Here, if I look at it, right, I can basically see that my P0, right, isn't quite done yet. I need to have another little chunk. P1 actually is done, right, so I can kind of forget about that. And then P2 needs a little chunk as well. And so in this case, right, I'll go back to everybody that still needs time and give them that time. So I go back, right, I skip P1, right, P0, right, I will give it some time, right, I'll give it another block of 5, and I'll give P2, that matches to this over here. And this one over here at P2, well, P2 has a little block, so I'll go ahead and basically consume that. And that's this one over here. The one's a little bit narrower than the other ones. So I have kind of now my little draft here, right, of how these things will run. So this is basically my round 1, right? So this is round 1, and this is my round 2. But I only have 2 things there, right? Because one of the processes, right, process 1 was satisfied with just the time I got from the first round. So that's how I break stuff up, right? If I have more processes, right, I might extend that, right? I would break that process up as well into chunks of at most 5, right? And then put them in this order, right? So the 0, 1, 2 order, right, is kind of the order I'm using within each round, right? Or ordered by process number. And then as process is complete, right, they're simply not included in future rounds. And this, right, will span out to the right as you get processes that are longer and longer. Okay, so let's say we have this picture here. Now we want to basically compute our completion times and our waiting times. And these will be a little bit more work than we had for the other scheduling algorithms, because you can see things a little bit interleaved. It's going to be a little bit more complicated. The one I'm going to start with is waiting time. So waiting time, right, is basically the time that a process sits around waiting for something else to happen. So let's take a look at this. First what I'm going to do is I'm going to calculate waiting time for P0. So I have P0, right, is basically over here, right, and over here. Maybe I'll clean my diagram just a little bit. We basically have our P0 is here and here. And I want to calculate the waiting time for that, right? Basically my terms there, my expression, are going to be one term for each of the things that is, processes that is in my system. So let's look at P0. P0 looks like for the first go, right, it's basically waiting, no amount of time, right? It's the first thing that runs. There's no waiting time there. I don't need to worry about it. But then what I need to do basically is look at both of these together, right? So I need to look at those two different chunks, right? It would be 3 if I had more. Look at them, right, and figure out what is the total waiting time among all of them. First one had no waiting time. The second one, though, has a waiting time of 10. So this one over here, right, P0 has a waiting time of 10. I guess I should actually, let me add in something really quick for you guys. There's the little breaks here, right? So this should be, 5, 10, 15, 20, right? That's our little breaks there to show little, times as we go through there. For P0, right, for that second chunk, I'm saying it's waiting 10. Now, if you look at the diagram, you see that it has 15 next to it, right? It starts at time 15. It doesn't start at time 10, but I'm saying its waiting time is 10. Well, the reason I say that is because over here, P0 was active, so it was doing stuff, right? So that isn't, P0's waiting time. If you were active, right, you aren't waiting. So I'm only going to count kind of the little space in between it, right, where I'm having something else, right? So where P0 and P2 run, that's what I'll consider to be waiting time, right? That's what I'll count up. I don't want to double count, when I run as my own waiting time. So the waiting time for P0 ends up being 10. So you can see that over here. All right. So we have our first process figured out. What about the next one? So we have P1. What does its waiting time look like? This one's waiting time is actually pretty straightforward. I only goes once, right? So I just look, P0, right, or P1. P1's over here. Well, that thing is basically waiting 5 units a time. So, well, it's going to be 5 units a time, right? It doesn't go a second time, so I don't need to worry about doing any additional math. It looks like it's pretty much just standalone. So that one's fine. Over there, I have basically my last value here, which is my 15. So that's my waiting time for process 2. So how do I calculate that? Well, process 2 is over here. So that one there, and then there's another chunk over there. So I got to basically add up the stuff that's before it. So the first part of P2 is basically going to be, P0 and P1 run before it. That's 10 units of waiting. Okay, that's fine. If I look at P2, right? P2, basically, if I look at kind of the new amount of time it's been made to wait, right? So I want to basically skip, the process that, the time it's running itself, right? Again, we don't want to double count. This, we've already kind of taken care of the fact that that's waiting time as well in the initial calculation. So I want to look at kind of the new waiting time, and the new waiting time is 5 units over there. So 10 plus 5, 15, that gives me this number over here. And so I can add those all up, right? I get a total of 30. 30 divided by 3 is obviously not 5, so I have a little bit of typo there, so let's fix that. This is actually 10. There we go. See, I can do math sometimes. But yeah, that's how I get our waiting time. So it's a little bit more involved than the other algorithms. Second thing we want to talk about is completion time. So for completion time, we're basically going to end up, kind of adding in what is the length of the process to each of these, right? So if the process is, takes, 10 units of time, well then, I can basically look at my waiting time. My waiting time is 10 and extend it, right? So I'm going to have to wait, plus this is going to take me this long to actually complete it. So each of these terms here, right, my 10, 5, 15, basically I just add them with sort of what I have over here for like, these are my run times, right? So somehow, right, maybe I can even write something like, it'll be 10 plus 10, right, where it's like 10 waiting time plus 10 length of the process, plus, 5 plus 5, because 5 was the length of the process, and then 5 is how long I waited. And then, for the last one, basically the process length is 8, so I can do 8, and then I waited for 15 units of time. That gives me 15. And if you add those all up, right, you get 10, 20, you get 20, 10, and 23, right, which are these numbers here. So we're just basically, we're able, right, to add these things here from the overall length of the process. We're able to add those to the waiting times we figured out. We get basically the completion times, and then we can average those, right, and get our final result. So it's a little bit more work than the other algorithms, but hopefully, right, if you think about it for a little bit, right, and kind of get the idea that, oh, you don't need to wait for yourself, twice, right? You're not waiting on yourself, right? You also don't need to wait for somebody else twice. Then you should be okay, right? You should be able to figure it out, not too bad. One note here, right, that we need to kind of talk about as a final thing is basically the selection of the time quantum, right, or the time slice. So here, right, we just arbitrarily assumed it to be 5. How do we pick that? We have to be a little bit careful. I can do different things. As kind of a little graphic here, I have brought back kind of the image from earlier on. This image over here is basically showing us the typical burst size that the CPU sees. So here, right, I can see that I have kind of a peak around here, blah, blah, blah. My 5 ends up being about here, right? So my 5 is, say, about there. What that's indicating to me is that my time quantum I've selected in the previous example is large enough to complete the bulk of the burst that would be asked for, right? So the most requests by programs will ask for something that's like this much, right? And that'll be able to satisfy it in one round. It's only going to be a few things that are much larger, right? And those few things that are larger, that'll take me more rounds, right? They'll have to go around it again and again and again to get sliced up in many pieces. But for most things, they'll be able to be completed in one go. So here's a couple questions for you guys. First of all, what happens if I make my time quantum too high? Think about that for 1 second. Well, if you make it too high, what happens is that you end up basically bottlenecking, right? So if you have maybe one process in there, right, that is really large, right, it requires 24 units of time. Well, if you make your time quantum that large, that process isn't going to be sliced into pieces, right? So everybody will basically have to wait for that one process of length 24 to run before everybody else can have their turn, right? So you'll basically reduce your response time, right? You'll increase waiting time for everybody. You'll slow down on stuff, right? So because you're basically allowing, right, for that one kind of outlier who's really large, you're allowing for them basically to hog up your CPU, right? And you don't want that. The idea of round robin is to divide up work evenly among the different processes that are active. So that would be a bad idea. Second question is, what happens if I make my time process too small? Is it a good thing or a bad thing? Think about that for one moment. Okay, so if I make it too small, I get kind of a similar problem in that I get degraded performance. What happens is that I'm basically, right, if I pick it to be really small, none of my processes will be able to complete in one time quantum, right? They'll need to basically go again and again and again and again. And remember, behind the scenes, this isn't really free. I'm having to pay basically a context switch price, right? So whenever I go from process 0 to process 1 to process 2, I need to basically change what is the code that's running on the CPU. How do I do that, right? It's going to be a little bit of time. Right? I need to basically change that PCB, right, that process control block to update to be something new. That's not free for me, right? So there's overhead every time I switch between different processes. So if I make my time quantum really small, everything will end up being cut into a whole bunch of little pieces, and all those pieces, right, will basically slow down my system because it takes that time to switch the context. So that's going to be an issue there. So ideally, right, what I want to do is basically pick my number to be large enough that most processes, right, the bursts that most processes generate, those can be completed in one go. That would be ideal, right? Then I won't have to have process too many context switches, right, between processes. And then if it's not too large, then I won't stall out when if anybody particularly large comes along. So we have to be a little bit careful there. But this chart kind of that shows the trend of what do the typical calls look like. That can help us out a lot. So here I think 5 is a pretty decent value that helps us kind of get a decent performance from the system.